The Oort Cloud, the boundary of our solar system and its mysteries. 1. Introduction. A brief overview of the solar system. The solar system, a vast and intricate gravitational dance, comprises the Sun and the celestial bodies that orbit it. At its center lies the Sun, a medium-sized star that provides the necessary light and heat to sustain life on Earth. Surrounding our star are 8 major planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, each with its own unique characteristics and mysteries. These planets are accompanied by numerous moons, dwarf planets like Pluto, and countless asteroids and comets. The solar system extends far beyond the planets we observe. Its structure is a reflection of the dynamic processes that shaped it over billions of years. The inner solar system, composed of rocky planets, contrasts sharply with the outer solar system, where gas giants reign. Each region offers insights into planetary formation and evolution, yet the boundaries of our solar system stretch even further, hinting at an enigmatic realm that remains largely unexplored. Introduction to the Oort Cloud concept. At the farthest reaches of our solar system lies the Oort Cloud, a theoretical shell of icy objects that is believed to encircle the solar system at a distance of about 1,000 to 100,000 astronomical units, AU, from the Sun. For context, 1 AU is the average distance between Earth and the Sun, approximately 93 million miles, 150 million kilometers. The Oort Cloud is thought to be the source of long-period comets that occasionally venture into the inner solar system, providing a glimpse into the primordial materials from which our solar system formed. Named after the Dutch astronomer Jan Oort, who proposed its existence in 1950, the Oort Cloud remains elusive. Unlike the well-defined orbits of planets and asteroids, the objects within the Oort Cloud are dispersed and difficult to detect, primarily due to their vast distance and small size. The cloud is divided into 2 regions: the inner Oort Cloud, or Hills Cloud, which is more spherical in shape, and the outer Oort Cloud, which is thought to be more elongated and comet-like in structure. The importance of studying the Oort Cloud. Understanding the Oort Cloud is crucial for several reasons. First, it holds clues to the early solar system's conditions and the processes that led to the formation of planets and other celestial bodies. The materials that make up the Oort Cloud are remnants from the solar system's infancy, essentially time capsules that can reveal information about the formation of our cosmic neighborhood. Second, the Oort Cloud plays a significant role in the dynamics of the solar system. The gravitational influences of nearby stars and the galactic tidal forces can perturb the orbits of Oort Cloud objects, sending some into the inner solar system as comets. Studying these comets can enhance our understanding of both the Oort Cloud and the broader gravitational interactions that govern the solar system's stability. Finally, the Oort Cloud has implications for planetary defense and the future of human exploration. As comets from the Oort Cloud can potentially collide with Earth, understanding their trajectories and origins is vital for assessing potential threats. Moreover, as space exploration advances, the Oort Cloud may become a target for future missions aimed at unraveling the mysteries of our solar system's boundaries. In summary, the Oort Cloud represents a frontier of knowledge, a boundary that challenges our understanding of the solar system and its origins. By studying this distant region, we not only seek to answer fundamental questions about our cosmic heritage, but also prepare for the challenges and opportunities that lie ahead in our exploration of the universe. As we delve deeper into the mysteries of the Oort Cloud, we are reminded of the vastness of our solar system and the endless possibilities for discovery that await. What is the Oort Cloud? Definition and description. The Oort Cloud is a theoretical construct that represents the outermost region of our solar system, believed to be a vast reservoir of icy bodies that orbit the Sun at an extraordinary distance. Named after Dutch astronomer Jan Oort, who proposed its existence in 1950, this enigmatic cloud is thought to extend from about 1,000 to 100,000 astronomical units, AU, from the Sun. To put this into perspective, 1 AU is the average distance from Earth to the Sun, approximately 93 million miles, 150 million kilometers. At such distances, the Oort Cloud is well beyond the orbits of the major planets and even the Kuiper Belt, another region filled with icy bodies. The Oort Cloud is not directly observable. Instead, it is inferred from the behavior of long-period comets that enter the inner solar system. These comets, often with highly elliptical orbits, are believed to originate from this distant cloud. The Oort Cloud is thought to contain billions, if not trillions, of icy bodies, ranging in size from small boulders to possibly dwarf planet-sized objects. Structure and composition. The Oort Cloud is generally divided into two distinct regions: the inner Oort Cloud and the outer Oort Cloud. This classification helps scientists understand the different characteristics and behaviors of the objects found within these vast expanses. Inner Oort Cloud, Hills Cloud. The inner Oort Cloud, sometimes referred to as the Hills Cloud, is a more spherical region situated between approximately 1,000 and 20,000 AU from the Sun. This area contains a dense concentration of icy objects, many of which are believed to be remnants from the early solar system. The objects in the inner Oort Cloud are thought to have formed in the vicinity of the giant planets and were later scattered outward due to gravitational interactions. One of the key features of the inner Oort Cloud is its relatively stable environment. The gravitational pull from the Sun, combined with the effects of nearby stars and the galactic tide, influences the orbits of these icy bodies. Some of these objects may eventually be nudged into trajectories that bring them closer to the Sun, resulting in the formation of long-period comets with orbits that can take thousands of years to complete. Outer Oort Cloud. The outer Oort Cloud is believed to extend from about 20,000 AU to as far as 100,000 AU. Unlike the inner cloud, which has a more spherical shape, the outer Oort Cloud is thought to be more elongated and diffuse. This region is less densely populated with icy bodies, and the objects within it are believed to be more loosely bound by the Sun's gravity. The outer Oort Cloud serves as a transitional zone between the solar system and interstellar space. The gravitational influences from nearby stars, as well as the tidal forces exerted by the Milky Way galaxy, can lead to perturbations in the orbits of these distant objects. Some of these gravitational nudges can send objects into the inner solar system, where they may become visible comets. Theoretical versus observed characteristics. While the existence of the Oort Cloud is widely accepted among astronomers, direct observational evidence remains elusive. This is primarily due to the vast distances involved and the small size of the objects in the Oort Cloud, which makes them incredibly difficult to detect with current technology. Theoretical models of the Oort Cloud are based on the observed behavior of long-period comets, which exhibit characteristics consistent with the cloud's predicted properties. For instance, the orbits of these comets are often highly elliptical, suggesting that they originated from a distant source. Additionally, the fact that many of these comets come from all directions supports the idea of a spherical distribution of icy bodies in the Oort Cloud. However, the lack of direct observations raises questions about the cloud's specific composition and structure. Some astronomers speculate that the Oort Cloud may contain a diverse array of materials, including water ice, ammonia, methane, and other volatile compounds. Understanding the exact nature of these objects is critical for piecing together the history of the solar system. The Oort Cloud also challenges our understanding of other planetary systems. Observations of exoplanets and their surrounding debris disks suggest that many solar systems may have similar outer regions, raising intriguing questions about the formation and evolution of planetary systems across the galaxy. In conclusion, the Oort Cloud represents a fascinating frontier of astronomical research. Its definition and structure provide insights into the solar system's formation, while its theoretical characteristics continue to inspire scientists to seek direct evidence. As technology advances, the hope remains that we will one day unlock the mysteries of this distant region and gain a deeper understanding of our cosmic neighborhood. 3. Historical context. Early theories about the solar system's boundaries. The concept of the solar system and its boundaries has evolved dramatically over the centuries. In ancient times, the solar system was viewed primarily through the lens of philosophical and mythological frameworks. The geocentric model, which placed Earth at the center of the universe, dominated for millennia, with celestial bodies revolving around it. This perspective limited the understanding of the solar system's true structure and extent. With the advent of the heliocentric model proposed by Nicolaus Copernicus in the 16th century, the understanding of the solar system began to shift. Copernicus suggested that the Sun, not the Earth, was at the center, and this revolutionary idea laid the groundwork for future astronomical discoveries. However, even with this new model, the outer boundaries of the solar system remained largely undefined. It was not until the 19th century that astronomers began to explore the possibility of regions beyond the known planets. The discovery of Neptune in 1846 was a pivotal moment in understanding the solar system's structure. The search for this planet was driven by irregularities in Uranus's orbit, which suggested the presence of another celestial body exerting gravitational influence. This successful prediction bolstered the idea that the solar system might extend further than previously thought, inspiring astronomers to consider additional, yet unseen realms. Contributions of key astronomers. Several key figures in astronomy contributed significantly to the concept of the solar system's boundaries and the eventual hypothesis of the Oort Cloud. Among these, Jan Oort stands out as a pivotal figure. In the mid-20th century, Oort's work on the dynamics of comets led him to propose the existence of a vast reservoir of icy bodies surrounding the solar system. Before Oort's hypothesis, the notion of a distant cloud of comets was not entirely new. In the 19th century, astronomers like William Herschel and others speculated about the existence of such a region. However, it was Oort who provided a comprehensive theoretical framework to explain the behavior of long-period comets. His research showed that these comets had orbits that were not confined to the plane of the solar system, suggesting a more spherical distribution of icy bodies in a distant cloud. Oort theorized that the Oort Cloud was a remnant of the primordial solar nebula from which the solar system formed. He proposed that the gravitational influences from nearby stars and the Milky Way galaxy could perturb the orbits of these icy objects, occasionally sending them into the inner solar system as comets. This hypothesis provided a cohesive explanation for the observed behavior of long-period comets and established a new understanding of the solar system's boundaries. Development of the Oort Cloud hypothesis. The formal development of the Oort Cloud hypothesis was a culmination of various astronomical discoveries and theoretical advancements. In the 1950s, Oort published his findings, detailing how the cloud could explain the origins of long-period comets. His work was groundbreaking in that it offered a unifying theory that connected the dynamics of the solar system with the behavior of comets. Oort's hypothesis gained traction in the scientific community, leading to further investigations into the nature of the Oort Cloud. Researchers began to explore its implications for the solar system's formation and evolution. The idea that the Oort Cloud could be a source of ancient materials, preserving clues about the solar system's early history, sparked interest in studying comets more closely. In the decades that followed, advancements in observational techniques allowed astronomers to gather more data on comets and their orbits. While direct observations of the Oort Cloud itself remained elusive, the study of comets helped validate Oort's predictions. The discovery of numerous long-period comets, whose orbits matched the expected characteristics of Oort Cloud objects, provided indirect evidence supporting the hypothesis. The Oort Cloud hypothesis also prompted scientists to consider the existence of similar structures in other planetary systems. As exoplanet discoveries accelerated in the late 20th and early 21st centuries, astronomers began to investigate the potential for Oort-like clouds around distant stars. This research opened up new avenues for understanding the formation and evolution of solar systems beyond our own. As technology continues to advance, the exploration of the Oort Cloud remains a tantalizing prospect. Future missions and telescopes may one day provide direct evidence of this distant region, enriching our understanding of the solar system's boundaries and the cosmic processes that govern its evolution. In conclusion, the historical context of the Oort Cloud is marked by a progression of ideas, discoveries, and key contributions from astronomers who sought to understand the solar system's structure. From Burley theories about the solar system's boundaries to Jan Oort's groundbreaking hypothesis, the journey to uncover the mysteries of the Oort Cloud reflects humanity's enduring curiosity about the cosmos. As we continue to explore and study this distant realm, we move closer to understanding not only our solar system's origins, but also the broader universe in which we reside. The formation of the Oort Cloud. Theories on how the Oort Cloud formed. The formation of the Oort Cloud is a topic of considerable debate and research in the field of astronomy. While the Oort Cloud itself remains theoretical, no direct observations of it have yet been made. It is generally accepted that it formed from the remnants of the solar system's early development. There are several prevailing theories regarding its origin, each highlighting different aspects of the complex processes involved in the formation of our solar system. One of the leading theories posits that the Oort Cloud originated from the protosolar nebula, the disk of gas and dust that surrounded the young sun about 4.6 billion years ago. During the early stages of the solar system's evolution, small icy bodies formed in this nebula. As the solar system developed, these bodies underwent a series of gravitational interactions, particularly with the giant planets, Jupiter, Saturn, Uranus, and Neptune. As these planets formed and migrated into their current orbits, they exerted significant gravitational forces that scattered many of these icy bodies outward. Some of these bodies were ejected into the far reaches of the solar system, while others became trapped in the gravitational influence of the sun, forming a distant shell of icy objects that we now refer to as the Oort Cloud. Another theory suggests that the Oort Cloud may have formed as a result of interactions with nearby stars. In the early solar system, stars were more densely packed in the regions of the Milky Way, leading to frequent encounters between stellar systems. These interactions could have perturbed the orbits of icy bodies, pushing them further away from the sun and into a more stable region, eventually leading to the formation of the Oort Cloud. Relationship to the solar system's evolution. Understanding the formation of the Oort Cloud is essential for grasping the broader evolution of the solar system. The processes that created the Oort Cloud are closely linked to the dynamics of planetary formation and the interactions between celestial bodies. As the solar system evolved, the gravitational influences of the giant planets played a crucial role in shaping the trajectories and fates of these icy objects. The formation of the Oort Cloud also reflects the complex interplay between the solar system and its environment. The early solar system was a chaotic place, with many collisions and gravitational interactions occurring. The scattering of icy bodies into the Oort Cloud illustrates how the solar system was not a static entity, but rather a dynamic system subject to external influences. Moreover, the Oort Cloud serves as a repository of information about the conditions that prevailed during the solar system's formation. The icy bodies within the cloud are thought to be remnants from the early solar nebula, preserving clues about the materials and processes that contributed to the formation of the planets. Studying these objects, particularly when they are perturbed into the inner solar system as comets, can provide insights into the solar system's history and the conditions of the early solar system. Role of gravitational interactions. Gravitational interactions are fundamental to the formation and dynamics of the Oort Cloud. The giant planets, particularly Jupiter and Saturn, exert significant gravitational forces that influence the orbits of nearby objects. During the early solar system's evolution, these gravitational interactions played a crucial role in the scattering of icy bodies. As the giant planets formed and migrated outward, they created a gravitational sculpting effect on the surrounding material. This process not only helped shape the orbits of the planets themselves, but also affected the trajectories of smaller bodies. Some icy bodies were ejected into the far reaches of the solar system, where they eventually contributed to the formation of the Oort Cloud. Additionally, interactions with passing stars and the gravitational tides of the Milky Way galaxy further influenced the stability and distribution of Oort Cloud objects. The gravitational pull from nearby stars can perturb the orbits of these icy bodies, nudging them into orbits that bring them closer to the Sun. This is how many long-period comets are believed to originate from the Oort Cloud. They are nudged into the inner solar system, where they become visible as they approach the Sun. The role of gravitational interactions extends beyond the formation of the Oort Cloud. Understanding these interactions is essential for predicting the behavior of Oort Cloud objects and their potential impact on the inner solar system. For instance, the gravitational influence of a passing star could send an Oort Cloud object on a collision course with Earth, highlighting the importance of studying this distant region. In summary, the formation of the Oort Cloud is a complex process that involves various theories and mechanisms. From its origins in the solar nebula to the gravitational interactions that shaped its development, the Oort Cloud is a testament to the dynamic nature of our solar system. As astronomers continue to study the Oort Cloud and its relationship with the solar system's evolution, we gain valuable insights into the origins of our cosmic neighborhood and the forces that govern its behavior. Understanding the Oort Cloud not only enriches our knowledge of the solar system, but also opens avenues for exploring the broader universe and the processes that shape planetary systems across the galaxy. 5. The significance of the Oort Cloud impact on our understanding of comets. The Oort Cloud plays a pivotal role in shaping our understanding of comets, which have fascinated humanity for centuries. These icy bodies are often viewed as messengers from the distant past, providing essential clues about the early solar system and the processes that led to the formation of planets. Comets that originate from the Oort Cloud are referred to as long-period comets, characterized by their highly elliptical orbits that can take thousands of years to complete. The study of these comets has revealed much about the composition and behavior of primordial material. When long-period comets approach the Sun, they develop tails and comas as they heat up, releasing gas and dust. This process allows astronomers to analyze their chemical composition, which often includes water, ice, carbon dioxide, ammonia, and organic compounds. Such analyses can provide insights into the conditions present in the solar nebula, helping to piece together the story of the solar system's formation. Moreover, the Oort Cloud serves as a reservoir of ancient materials. As comets enter the inner solar system, they act as time capsules, preserving information about the solar system's early environment. By studying the isotopic ratios and chemical makeup of cometary material, scientists can glean insights into the conditions that existed 4.6 billion years ago when the solar system was forming. This information can help us understand the processes that led to the emergence of life on Earth and potentially on other planets. Role in the solar system's dynamics. The Oort Cloud is not just a distant collection of icy bodies. It plays a crucial role in the dynamics of the solar system as a whole. The gravitational influences of the Oort Cloud extend beyond its boundaries, affecting the orbits of objects throughout the solar system. As Oort Cloud objects are perturbed by gravitational interactions, whether from passing stars or the tidal forces of the Milky Way, they can be nudged into the inner solar system, leading to new trajectories and orbits. This gravitational interplay is essential for understanding the long-term stability of the solar system. The Oort Cloud acts as a buffer zone, absorbing and redistributing the effects of external forces. By studying how these interactions influence the trajectories of comets and other bodies, astronomers can gain insights into the long-term evolution of the solar system. Additionally, the Oort Cloud may also be linked to the periodicity of comet showers, which have been observed throughout history. Some researchers hypothesize that the gravitational perturbations caused by nearby stars or the galactic tides can trigger a wave of comets entering the inner solar system, leading to increased activity. Understanding these dynamics can illuminate the patterns of cometary activity and enhance our predictions of future comet appearances. Importance for future space missions. The significance of the Oort Cloud extends into the realm of space exploration, offering tantalizing prospects for future missions. As technology advances, the Oort Cloud may become a target for exploration, providing opportunities to study its icy inhabitants up close. Understanding the Oort Cloud could yield insights not only into our solar system, but also into the broader processes that govern planetary systems throughout the galaxy. One of the key motivations for exploring the Oort Cloud is the potential to uncover new scientific discoveries. Missions targeting Oort Cloud objects could provide direct samples of primordial material, allowing scientists to analyze their composition and gain first-hand knowledge of the conditions present during the solar system's formation. Such missions could help answer fundamental questions about the origins of water, organic compounds, and other building blocks of life. Moreover, studying the Oort Cloud can inform planetary defense strategies. The gravitational dynamics of Oort Cloud objects can pose a potential threat to Earth if they are nudged into orbits that bring them close to our planet. By understanding the characteristics and trajectories of these objects, scientists can develop models to predict potential impacts and devise strategies for mitigation. Lastly, the exploration of the Oort Cloud aligns with humanity's broader quest to understand our place in the universe. As we venture beyond the confines of our immediate solar system, the Oort Cloud serves as a gateway to the cosmos. It represents the boundary between our solar system and the vast interstellar medium, offering a unique opportunity to study the transition between solar and interstellar environments. In conclusion, the significance of the Oort Cloud is multifaceted, impacting our understanding of comets, the dynamics of the solar system, and the prospects for future space missions. By studying this distant region, we can unlock valuable insights into the origins of our solar system and the processes that govern celestial bodies. As we continue to explore the mysteries of the Oort Cloud, we not only deepen our knowledge of our cosmic neighborhood, but also lay the groundwork for future exploration and discovery in the vast expanse of the universe. The Oort Cloud stands as testament to the complexity and beauty of the solar system, inspiring scientists and explorers alike to reach for stars. 6. Mysteries and challenges. Current unanswered questions about the Oort Cloud. Despite significant advances in our understanding of the Oort Cloud, many questions remain unanswered, underscoring the cloud's enigmatic nature. One of the primary mysteries is the exact composition of the Oort Cloud. While it is generally accepted that the cloud consists of icy bodies, the specific materials and their distributions within the cloud are still largely unknown. Are these bodies primarily made of water ice, or do they contain complex organic compounds? Understanding the composition is crucial for piecing together the conditions that prevailed during the solar system's formation. Another significant question concerns the dynamics of the Oort Cloud itself. How stable is this distant region, and how do the gravitational influences from nearby stars impact its structure? Current models suggest that Oort Cloud objects can be perturbed by the gravitational pull of passing stars, but the frequency and impact of these interactions remain uncertain. Additionally, how many objects exist within the Oort Cloud? Estimates range from billions to trillions, yet the actual number could be vastly different from current predictions. The relationship between the Oort Cloud and the Kuiper Belt is another area of active research. While both regions are thought to contain icy bodies, they differ in their locations and dynamics. Understanding how these two regions interact and influence one another could provide insights into the early solar system's evolution. Furthermore, how do Oort Cloud objects relate to the periodicity of comet showers observed from Earth? Unraveling these connections could shed light on the mechanisms that drive cometary activity. Difficulties in studying the Oort Cloud. Studying the Oort Cloud presents a unique set of challenges, primarily due to its vast distance from the Sun and the small size of its constituent bodies. The Oort Cloud is located at a staggering distance of up to 100,000 astronomical units, AU, making it incredibly difficult to observe directly. The faintness of the objects within the cloud, combined with their great distances, means that they are not detectable with current telescopes and instruments. Moreover, the Oort Cloud does not emit light in the same way that many celestial bodies do. Instead, its objects are primarily observed when they are perturbed into the inner solar system, where they become visible as comets. This indirect approach to studying the Oort Cloud complicates the collection of data, as astronomers must rely on observing the behavior of comets rather than directly studying the cloud itself. Another challenge lies in the long timescales involved in studying the Oort Cloud. Many long-period comets take thousands of years to complete their orbits. This means that any predictions about the cloud's dynamics or composition are subject to significant uncertainty. Additionally, the time required for an object to travel from the Oort Cloud to the inner solar system can span generations, making it difficult for scientists to observe and study these phenomena within a human time frame. The search for observational evidence. The quest for observational evidence of the Oort Cloud is ongoing, driven by the desire to confirm its existence and better understand its properties. Several strategies are being employed to gather data, but each comes with its own challenges. One approach is to study long-period comets that are believed to originate from the Oort Cloud. By analyzing their trajectories, chemical compositions, and physical characteristics, astronomers hope to glean insights into the cloud's nature. Advancements in technology, such as the development of more powerful telescopes and space-based observatories, offer promising avenues for exploration. Instruments like the James Webb Space Telescope, JWST, and future missions designed to survey the outer solar system could provide crucial data. These telescopes may be able to detect faint signals from Oort Cloud objects or capture images of long-period comets, enhancing our understanding of their origins and the cloud itself. Another avenue of research involves computer simulations that model the dynamics of the Oort Cloud. By simulating the gravitational interactions between Oort Cloud objects and nearby stars, scientists can develop predictions about the cloud's structure and behavior. These models help inform observational strategies and guide future explorations. Despite these efforts, the lack of direct observational evidence remains a significant hurdle. The Oort Cloud's vast distances and the faintness of its objects mean that much of the ongoing research relies on indirect evidence and theoretical models. As a result, the scientific community continues to grapple with the challenge of confirming the existence of the Oort Cloud and understanding its intricate dynamics. In conclusion, the mysteries and challenges surrounding the Oort Cloud reflect the complexities of studying a distant and elusive region of our solar system. From unanswered questions about its composition and dynamics to the inherent difficulties in observational research, the Oort Cloud remains a frontier of astronomical inquiry. As scientists continue to explore this enigmatic region, they are driven by the hope that one day, direct evidence will illuminate the nature of the Oort Cloud and its role in the broader narrative of our solar system's history. 7. Future research directions, upcoming missions and technologies. As our understanding of the Oort Cloud continues to evolve, the next decade promises exciting advancements in research and exploration. A variety of upcoming missions and technologies are poised to significantly enhance our ability to study this enigmatic region of the solar system. Among the most anticipated is the launch of new space telescopes and probes designed to gather data on distant celestial bodies, including those believed to originate from the Oort Cloud. One such mission is NASA's Lucy, which is set to launch in 2021 and will study Trojan asteroids, but its findings could provide insights into the early solar system and inform our understanding of the Oort Cloud. While not directly targeting the Oort Cloud, the data collected could help refine models of solar system formation and the evolutionary pathways of icy bodies. Another promising mission is the European Space Agency's ESA Comet Interceptor, which aims to explore a comet that has never before entered the inner solar system. This mission, planned for launch in the mid-2020s, will allow scientists to study pristine cometary material, potentially offering insights into the composition of Oort Cloud objects. By examining these ancient materials, researchers hope to uncover clues about the solar system's formation and the conditions that existed during its early history. The role of telescopes and space probes. Ground-based and space-based telescopes are crucial for advancing our understanding of the Oort Cloud. Observatories equipped with advanced instruments are capable of detecting faint comets and other distant objects. The James Webb Space Telescope, JWST, launched in December 2021, represents a significant leap in our observational capabilities. With its powerful infrared capabilities, JWST is expected to provide unprecedented views of distant ice bodies, including those in the Oort Cloud. JWST's ability to analyze the chemical composition of comets will be invaluable in understanding the materials that make up Oort Cloud objects. By examining the signatures of various compounds and isotopes, astronomers can piece together the history of these icy bodies and their role in the solar system's evolution. In addition to JWST, ground-based telescopes like the Large Synoptic Survey Telescope, LSST, scheduled for completion in the mid-2020s, will play a pivotal role in scanning the night sky for transient objects, including comets. The LSST's wide-field survey capabilities will allow it to detect and track a multitude of comets, providing essential data for understanding the dynamics of the Oort Cloud and the origins of long-period comets. Space probes also hold great potential for advancing our knowledge of the Oort Cloud. Future missions, designed to study distant comets, will allow scientists to gather direct data from these icy bodies, providing insights that ground-based observations cannot. Probes like NASA's New Horizons, which famously flew by Pluto, may be repurposed for future missions to explore other distant objects, possibly including those from the Oort Cloud. Predictions for discoveries in the next decade. The next decade is poised to yield significant discoveries related to the Oort Cloud and its implications for our understanding of the solar system. With advancements in observational technology and upcoming missions, researchers anticipate uncovering new insights into the composition, dynamics, and origins of Oort Cloud objects. One anticipated development is the potential discovery of previously unseen Oort Cloud objects. As telescopes become more sophisticated, the ability to detect faint, distant bodies is expected to improve dramatically. Another area of exploration will focus on the interactions between the Oort Cloud and nearby stars. Ongoing research into the gravitational influences of passing stars and the effects of galactic tides could yield new insights into how these factors shape the dynamics of the Oort Cloud. Understanding these interactions will be crucial for predicting the behavior of Oort Cloud objects and their potential impact on the inner solar system. Finally, the study of the Oort Cloud may contribute to our understanding of exoplanetary systems. As astronomers discover more about the architectures of distant solar systems, comparisons with our own solar system, including the structure and dynamics of the Oort Cloud, will help reveal universal patterns in planetary formation and evolution. In conclusion, the future of Oort Cloud research is bright, with upcoming missions, advanced technologies, and innovative telescopes poised to transform our understanding of this distant region. As we embark on this journey of exploration and discovery, the Oort Cloud holds the promise of revealing fundamental truths about the origins of our solar system, the nature of comets, and the broader processes that govern celestial bodies throughout the universe. The next decade may very well be a turning point in our quest to unravel the mysteries of the Oort Cloud and its significance within the cosmic tapestry. Conclusion summary of key points. The Oort Cloud, a theoretical shell of icy bodies surrounding our solar system, represents one of the final frontiers of astronomical research. Its existence, proposed by Jan Oort in the mid-20th century, offers crucial insights into the formation and evolution of the solar system. The Oort Cloud is generally divided into two regions: the inner Oort Cloud, Hills Cloud, and the outer Oort Cloud, each playing a distinct role in the dynamics of our solar system. The formation of the Oort Cloud is believed to have resulted from the gravitational interactions of icy bodies in the early solar system, particularly influenced by the giant planets. This cloud serves as a reservoir for long-period comets, which provide valuable information about the primordial materials that formed our solar system. Despite advancements in our understanding, many mysteries remain surrounding the Oort Cloud. Questions about its composition, the number of objects it contains, and its interactions with nearby stars persist as key areas of inquiry. The challenges of studying this distant region, primarily due to its vast distance and the faintness of its objects, complicate our efforts to gather direct observational evidence. The Oort Cloud's relevance to broader astronomical studies. The significance of the Oort Cloud extends far beyond merely enhancing our knowledge of our solar system. Its study is intricately linked to broader astronomical themes, including planetary formation, the dynamics of celestial bodies, and even the potential for life beyond Earth. The materials contained within the Oort Cloud are believed to be remnants from the early solar nebula, preserving essential clues about the conditions that existed when our solar system was forming. Furthermore, the Oort Cloud has implications for understanding exoplanetary systems. As astronomers discover more about the architectures of distant solar systems, comparing those systems with our own, including the structure and dynamics of the Oort Cloud, can reveal universal patterns in planetary evolution. This comparative analysis enriches our understanding of how solar systems form and develop over time. The Oort Cloud also plays a role in planetary defense. Understanding the dynamics of Oort Cloud objects is crucial for predicting potential impacts on Earth. As comets are perturbed into the inner solar system, knowing their trajectories can inform strategies for mitigating potential threats, ensuring the safety of our planet. Final thoughts on its mysteries and future exploration. As we look to the future, the mysteries of the Oort Cloud continue to captivate scientists and astronomers alike. The next decade promises to bring significant advancements in technology and observational capabilities, opening new avenues for exploration. Upcoming missions such as the ESA's Comet Interceptor and NASA's ongoing research into comets are set to provide unprecedented insights into the nature of Oort Cloud objects. The role of advanced telescopes, like the James Webb Space Telescope and the Large Synoptic Survey Telescope, will be instrumental in detecting and analyzing faint objects from the Oort Cloud. These technologies hold the potential to transform our understanding of this distant region, allowing us to explore the origins of comets and their implications for the solar system. Moreover, the collaborative efforts of the global scientific community will be crucial in unraveling the mysteries of the Oort Cloud. As researchers from various disciplines come together to study this elusive region, we will deepen our understanding of not only our solar system, but also the broader universe. In conclusion, the Oort Cloud stands as a testament to the complexity and beauty of our cosmic neighborhood. Its study is not merely an academic pursuit. It is a journey into the past that informs our understanding of the future. As we continue to explore the Oort Cloud and its secrets, we remain ever more connected to the universe and its mysteries, driven by the enduring human quest for knowledge. The Oort Cloud invites us to ponder our origins and the infinite possibilities that lie beyond, inspiring future generations to reach for the stars. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.